Okay, real quick, let's get through example of this, and then I want to show you how to do a couple problems on the last assignment, and then you just work and to get questions answered. So how about one like this? Now, there's one like this on the assignment. This is pretty standard kind of physics question. So think what's going on here. Person's riding a bike around a circular corner at 12.5 meters per second. The radius of the turn that they're trying to make is 25 meters. So we want to know what's the minimum coefficient of static friction. So before we do this, real quick, you know centripetal acceleration is not a specific force. It's not like weight or tension or friction or something like that. Centripetal acceleration is just a category of forces that cause an object to move in circular motion, uniform circular motion, right? Uniform circular motion just means constant speed in a circle, right? Okay, so it's a category, it's not the specific agent of the circuit that's causing the circular motion, right? It's just the category of forces that could cause that, not the specific one. So centripetal force could be tension. If you've got a rock on a piece of string and you're spinning it around, then the centripetal force is provided by the tension in the string. If you're talking about like an orbital problem, where you've got a satellite orbiting a planet, well then the centripetal acceleration or centripetal force is provided by gravity, force of gravity, right? It's the weight of the object that's causing it to move in a circle. What about this case here? What's causing the bike to move in a circle? Friction. And a good way to kind of prove that to yourself would be to say, okay, well, what if you removed friction? What if you had an icy surface and you sprayed it with WD-40? Could the person make the turn then? No, they just would go straight regardless, right? They couldn't generate friction to make themselves move in a circle, right? So it's the friction is what's providing the centripetal force. So if we wanted to draw a free body diagram here, it's just a little bit different than what we're used to, because the reason it's different is because this time the force isn't all happening in a straight line, it's happening in a circle, right? And so when we draw the picture, the free body diagram, it's going to look like, well, you tell me. Here's the object. What are the forces acting vertically on the bike? Gravity. So weight is pushing down, mg. Normal force is pushing straight up, isn't it? Right? Because it's a level road. And what's the other force acting here? Friction. It's acting in which direction? To the whichever. If the center of the circle is over here, then it's pointing towards the center of the circle, right? And is it static or kinetic? It's static. How come it's static and not kinetic? It seems like it'd be kinetic. It's moving. Well, no. Because think what the static or kinetic means for friction. Static means the two surfaces are not sliding. Kinetic means they are sliding. Well, the tire's not sliding, it's rolling, right? So it's static frictional force. That's our free body diagram. So we can break this down, just like before, we can break this down into our equations of motion. So if we want to look at the net force, at the horizontal component of the net force. So I could call this, the vertical component of the net force. So I could call that net force sub y. The y component is still really the y component, isn't it? What are the two? So when we're adding up a net force, we're just consolidating or adding up all of the forces that act vertically or have components that act vertically. So what are they? So normal force is positive. We should start with the positive ones. So normal force points up, so that's a positive force acting in the y direction. Then what? Minus mg. Now what's that going to be equal to? 0. How come? Okay, but why? How do we know that? But now imagine this in your head. This guy's going around in a circle on a bike. It's not accelerating up or down, right? It's staying at the same height the whole time, right? It's the only acceleration is going to be the centripetal acceleration. So we know that's 0. So there's equation 1, right? Equation 2. Now let's look at what are we gonna call this one, the X component? The X component's really not a great way to say it, because X is a specific direction. This is really the centripetal force, isn't it? Right?
Yeah.
So if we wanna say the net force in the horizontal direction, it probably would be in the centripetal direction, I guess you would say. You technically, I guess you could call it X because it's horizontal, but really what you're looking for here is the centripetal force. That's the only force acting horizontally, right? So what is the centripetal force? What's providing it? That's the category.
V squared over R.
Okay, well, that's what centripetal acceleration is, but what kind of force is acting centripetally here? Friction, right? So the only force we get is static frictional force, right? And that's equal to our centripetal force equation. Well, we know that centripetal force is really just equal to, right, it's right here, I guess. Centripetal force just equals mass times centripetal acceleration, right?
Mm-hmm.
And what's centripetal acceleration, Delaney?
V squared over R.
V squared over R is one expression for it. And that's the one that we want to use because we've got a V and an R, right?
Mhm.
So that's equal to M V squared over R. And so there's our other equation. Right? There's equation 2. We know that the frictional force is the centripetal force. Okay? So we know that now we have to kind of combine these things, right? What's our equation for a frictional force?
Mr. Leo?
Yeah.
Can you go back and say how you got the MV squared over R?
Sure, because we know that centripetal force, by definition, centripetal force is nothing more than mass times centripetal acceleration, right? Newton's second law applied to centripetal forces, right? And we know that A sub C, right, centripetal acceleration is, we found out, remember we did that big geometry proof on the board and we found out it was V squared over R, right? Okay, so we can make that substitution. And so now if we substitute for, we know, so I think somebody said it, what is our equation for a frictional force? Mu times normal force, good. So we get mu sub s times normal force must equal mv squared over r. But from our first equation up here, if I solve for normal force, what do I get? mg. If I isolate normal force, right? So we can make that substitution. Makes sense, doesn't it? Because the only forces acting vertically are normal force and weight. They're acting in opposite directions, so they must be equal and opposite, right? So then if we make that substitution, we get mu sub s times mg equals mv squared over r. I'm really just trying to isolate the mu, aren't I?
Yep.
Anything else I can do there?
Cancel the m's.
Yeah, I can divide both sides by m to cancel those. And then the last step would just be to divide both sides by g, which is the same thing as multiplying by 1 over g, isn't it?
Mm-hmm.
So if I do this, we got our answer, right? Okay, so then we end up getting mu sub s equals v squared, so that's 12.5. I want to put the units in for a second so you can see something. Meters per second, quantity squared, over 9.8 meters per second squared times 25, was it 25.0? Yeah, 25, just 25 I guess, huh?
Where did you get the V squared over R and V squared over R? Where did that whole thing come from?
That's just, there are 3 equations. I'll put them on the next page because we're going to need them on the next page anyway. There are 3 equations that we really use for centripetal acceleration for now. I mean, later on, when you guys do more intense angular physics in college, and maybe at the end of the year we'll come back and look at it, we could write it in terms of some angular velocity and things like that, right? But for now, we don't need to do that. Okay, it's also equal to centripetal acceleration. We could also write it this way. It's r times centripetal, or times angular velocity squared. But we haven't talked about angular velocity yet, and that's not important. So for us right now, the only equations we have are this. We know the basic one, kind of the basic centripetal force equation is or centripetal acceleration equation. Centripetal acceleration equals v squared over r. Okay, but we also know that if we want to talk about speed and write that in terms of radius and period, speed is just distance over time, right?
Mhm.
So we can calculate a speed by just dividing the distance an object travels by the time it takes to travel that. And we know that for uniform circular motion, the speed is constant, right? It's not speeding up and slowing down. It's constant speed in a circular path. So then couldn't we say that the speed is equal to,
2 pi.
yeah, how could we think of, what is a convenient unit of distance for which we know the amount of time required?
Wait.
How long does it take to make one lap? Well, by definition, that's period, right?
Yes.
And what is one lap around there in terms of r? Well, that's just circumference. The circumference of a circle is 2 pi r, right? So there's a relationship that relates v and r and t. And if we make that substitution, look what happens. If we make that substitution, we just get the quantity 2 pi r squared, 2 pi r over t squared, right, over r, which is 4 pi r squared over t squared divided by 1 over r. So if I flip and multiply, I'll get 4 pi r squared over r t squared. So one of the r's cancels, right? You don't have to do all that stuff. You can just remember this if you want to, because we use it a lot. So the other way we could write it is 4 pi, should be pi squared, shouldn't it? 4 pi squared r over t squared. Those are the three equations. That's it for centripetal acceleration. Those are the three you need to know. Okay? So that's where that one comes from. Long answer to a short question, right?
Like a
And so
politician.
where did the M come from?
Wait, can you go back?
Sure. To that one?
Oh.
Yeah.
You were right.
Those are just in your book on page something. And I'll update. Did I give you guys a little physics? I gave you a little physics formula sheet thing a while ago, didn't I?
Yeah.
I'll update it with the new stuff and give that to you.
My head is stronger.
Okay, we done with that one?
Yeah.
Okay, so then the question is, where did the M come from?
No.
Yeah.
Oh.
These are units here, right? You guys get that? Those are just units.
Yeah.
I put the units in. This is a mass, right? Because it came from the fact that, yeah, from right here.
So where'd you get
Which
that
one are you
M
looking-
from? The very top, because it was mu sub s Fn, and then Fn equals mg.
mg, right, exactly, yeah. And centripetal force is mass times centripetal acceleration, so it's m times v squared over r.
Is F centrifugal kind of equal to net force?
Say it again?
Is F centrifugal equal to like net force?
Well, it's equal to the, yeah, it is, it's equal to the,
So like we took out circular, it would be the net force.
yeah, it is, but now, think about this, so, but it's kind of different than before, because it's always pointing towards the center,
Mhm.
right? It might even be the result of more than one thing sometimes. I mean, let's just say, what's an example of that? If you had, I don't know, that'd be hard. Well, okay, yeah, we'll do one later, but this is for later. Where when you're writing on a banked circular turn, why do they bank turns?
What does that mean, bank?
Banked turn means like when you go around the turn, it's like on an indoor track. They put it up at an angle. Why do they do that? Okay, so you don't fly off. But what are they, in terms of the physics, what's the advantage of banking a turn?
Banking, you have to worry about. You know how like what you were saying, how like if you want to turn, it doesn't want you to turn, it wants you to keep going straight. If it's like angled, then it kind of forces you to go that way.
Okay, and if you think about it in terms of the physics, the main reason is because when something is on an angle, right? And I, like I say, we'll do a problem like this, but I don't want to throw it at you now. But like this is let's say this is a cross section of the turn, right? So the turn is built up, so you're going to be running into the board along that turn. There's the object. So gravity points straight down, right? Okay, so then there is a component. Well, think of it. Then the normal force points up like this, right? Agreed? So the normal force and the gravity, and maybe there's even still some friction, right, pulling you towards the center. So maybe there's some friction that's pushing you down the hill like that, let's say, right? Okay, there is going to be a component of the friction that's going to act towards the center of the circle, right? There's going to be a component of the normal force that acts towards the center of the circle, right?
Gravity doesn't act.
And gravity just acts straight down, right? But you see what I'm saying here? So the reason it's tilted like that is so you get both a frictional component, like when you're running around the track, you still would have to lean a little bit, right, and push on the track. But you also get a component of the normal force that's pushing you towards the center of the track as you run around this thing, right?
So it doesn't slow you down?
Well, because it's pushing, theoretically it doesn't, because it's pushing always perpendicular to your direction of motion. So it's not pushing against you, right? Okay, but you do, it does slow you down. It changes your mechanics a little bit. Yeah. Okay, so you get the idea? So you could even have multiple, but so then what's the centripetal force? When we added up the centripetal force here, we'd have to say, okay, well, it's going to be, we're not going to do this now, but there'd be a component based on this angle theta. There'd be a component of friction contributing to the centripetal force and a component of normal force contributing to the centripetal force. So it is like a net force, isn't it?
Okay.
Yeah. Right? So does this make sense then? We would just, whatever this turns out to be, like 0.6-ish, something like that. So that we're going to get, that's going to be our coefficient. Notice how the units cancel. We get meters squared per second squared divided by meters squared per second squared. They all cancel, right? And they should, because coefficients are unitless,
Yep.
right? Okay.
Except you have to fix that. In the assignment.
All right, so last one. There's no calculations. You're gonna like these.
I know, but I'm not sure.
These guys.
Yeah.
Oh, we went over.
Yeah, but it was a lot easier than when you went over because it was all ones.
Well, a lot of them are ones, but the one, I don't know I think you had one on there that was messed up, but I fixed them.
Okay.
So let's just make sure you know how to do this. So what is this asking us here? Can everybody read that okay? Do I need to make it bigger?
I can read it.
Okay. Oh, that's pretty small. I can make that a little bigger. How's that? That's good, huh? Okay, so now these, I want to show you how these are really pretty easy questions. All these are asking you to do is just look at how the proportionalities relate to each other. Or find proportionalities, I should say. Okay, let's do constants in red and variables in green. So the velocity is being quadrupled. So velocity is changing. That's a variable. What's being held constant? Mass and radius are being held constant. Okay, and so we want to know, what about period? How is the period of the ball changed? Is it changed? By what factor is it changed, right? So,
Can it not change because the radius doesn't change?
okay, so now what's the equation that's gonna be useful to us? We wanna find an equation that involves only the variables that whose behavior we know, right? So we're relating velocity and mass is really, mass isn't gonna be it, right? Mass doesn't even show up in any of these. The only equation mass shows up in is this one. Centripetal force equals mass times centripetal acceleration, right? So we'll ignore that one. But we've got velocity, radius, and period. So it's that one, isn't it? Right? So now look what that's saying. Let's copy that one down again. So we've got velocity is equal to 2 pi, which is a constant, times r over t. So I'm just going to say it's proportional to the ratio of r over t, right? Okay, well, what's going on there? We know that velocity is being quadrupled, so velocity is being increased by a factor of 4. Okay, on the other side, we get what?
Radius is the same.
Radius is the same, so that's being changed by a factor of 1. It's being multiplied by 1,
So how do
and we're
we-
solving for t. Well, by what factor would t have to change?
1/4?
1/4, wouldn't it? Right? If the top is being held constant, 1 divided by what would equal 4? 1/4, right? Okay, so t would have to be, so that answer is 1/4, right?
Yeah.
Okay, so once we get that, now that we know that t is changing by a factor of 1/4, what about acceleration? Well, we could use either one of these, couldn't we? Because we know the behavior of velocity, or speed I should say, speed and radius, and we know the behavior of radius and period. So you take your pick, they're both gonna give me the same answer. Thank you.
Do the first one, it's less earlier.
So if we wanna find acceleration then, centripetal acceleration is gonna be proportional to, let's just do this one, how about, v squared over r. So v is staying constant, isn't it?
Yeah.
Right, so that's gonna
V
be-
is quadruple.
Oh, never mind, it's quadrupling. So it's being changed by a factor of 4,
Squared.
but squared, right? Over r, which is staying the same. So in order for centripetal acceleration has to be proportional to that ratio, so it must be changing by a factor of 16. See what I'm saying? And then what about the force? Well, mass is not changing, so however acceleration is changing, force would have to change the same way, right? Okay, so that's also gonna be 16. Okay?
Got it.
I like these.
Yeah, you get the idea? Let's do just one more of those. I won't even write on it. You just tell me. So how about this one? This time the radius is tripled, right? So we know r. Whoops. So here's r. Radius is tripled, increased by a factor of 3. Mass and velocity remain unchanged. So velocity is unchanged. So we're going to use that second equation again, aren't we? We're going to use v equals 2 pi r over t. And let's see, the r is constant.
No,
ours.
ours
Oh,
tripled.
r's triple. I always do that. So we get
3.
v is proportional to 3 over, that should be a green 3, shouldn't it? Over t, which is,
The velocity is.
Oh.
Velocity is 1.
That's why you were using red. You're just
Yeah,
using
exactly.
velocity, you did radius.
so v stays the same, right? So 1 is proportional to 3 over
3.
t. So what would t have to be?
3.
3, right? 3 divided by what is 1? See how that works? These are really cool problems to me because you don't have to do any calculations, right? You're just looking at relationships. And then once you get these, once you know t and r and v, acceleration is pretty simple.
Wait, why did 2 pi get to go away?
Because it's a constant. right? So we know it's like in an equation, proportionality. Go back to like algebra 2. Remember that if we have proportionality, it just looks like this. Y equals some constant, could be 3, could be anything, right? Some constant times x. If x doubles, then so does y, right? So another way of saying that is just y is proportional to x. If you use the proportionality though, then you can get rid of all the constants and you can just think of the behavior. See what I'm saying? Why that's makes it a little simpler? Okay? You good? Go.